Sorry, just got started. Okay, that's cool. Yeah, let's take it away.
Yeah. All right. Let's get started. So today chapter is chapter 3 of the book, which talks about classification. And this is some of the content of the chapter that I managed to put down here. So the chapter is basically on classification, and the previous chapter we have seen regression, and the classification we're going to see 4 different kind of classification: binary classification, which do some kind of classification between 2 category, or 1 and 0, stuff like that. And we have multi-class classification, which do some kind of more than 2 classification. For instance, we can classify digit into 1 to 10. That's an example of one multi-class. Binary classification, we can classify something between 1 and 0. We can also have multi-level classification, where we can have different level. For instance, we have we want to classify paces of people. They have different levels, stuff like that. And lastly, we will see multi-out classification. Along with different kind of classification, the chapter talks about performance measure. So when we do the classification, how can we measure the performance of our classification algorithm? The chapter explored different kind of measures, such as accuracy, precision and recall, confusion matrix, F1 score, and ROC curve. So I assume, like, when we go to the chapter, let's I want the form to be like chart, so that we can walk through along. If someone has a more idea when I speak about something, you can chime in and talk about. Yeah. So the first thing first is about the data set we're going to use. So the data set we're going to use is MNIST, which is basically the hello world of machine learning. As they said, it is basically used as everyone beginning to learn machine learning. And the data set is about 70,000 small images of handwritten images. And now the easiest part of it for us to get the data set, Scikit-Learn provide a helper function that we can actually load the data sets from OpenML. So it's very easy to do that. So the previous book, as they said here, this function often fetch OpenML return pandas data frame, but the book is actually using returns dictionary. So when we put this argument as false, then we're gonna return dictionary, not data frame, because the function return by default data frame. So this one here, as you can see, we import the this fetch ML, and we have the keys here. We can see we have the data, we have the target, and many stuff like that. What we are interested in is actually, as we know, we have the data and the target, and here we can have using this, we can have the data, and this is the shape. We can see we have 70,000, and this are the targets. As you can see here, they said each image consists of 784 features, because each image contain 28 by 28 pixels. So 28 by 28 give us 784. That is that about that. So this is basically our what the data set is. Right. So let's move on and see some sample of digit from the data set. What can we see? How can we see a sample, one of the digit from the data set? So using matplotlib here, here we can see we have some digits, which is the data. We have this, what would mean the first digit here, and also we can reshape the digit here, as you can see by these pixels, and now we can show the digit. So the first digit here is somehow kind of looks like 5, which is of course 5, as we can see in the data section. This looks like 5, and in this is what it is. So if we look at this here from our target, we can see that y naught of 5 is 5. So But looking at this, we can see our data is in form of string. So we need to change the whole data and to preferable form that we can use to train machine learning, not in string format. And that's why here we use this to change the type of these, the target, which actually now we have turned it into an integer. So this is basically about the data set and looking at the sample of the data set. And also here, this is basically looking at the few digits from the whole data set. So there we just look at one example of the data set, but here we want to look at some example of the whole data set. So you can see here the code and writing the function here with this float digit, and here we have the sample. As you can see, this is the sample of the data set, and you can see the first one here is 5. So this basically just to show us how the sample of the data set. Any question? All right, okay, so now we have the data set at hand. Before any task in machine learning is to have what we call test and train set, test set. So we need to divide the data set as we have into train and test set. But luckily, the data set, MNIST data set, is already divided into test set and train set. So what we basically need to do is to just assign what will hold our test set and train set. So this one here, we actually assigning this X train, X test, Y train, and Y test. We assign the values. So we need not to call the function from Scikit-Learn that actually divide the data into train and test set, because the data is already divided into train and test set. But one thing we can also do is we need to shuffle data. So shuffling data is really important in machine learning tasks, because some algorithms take into cognizance about the order of the training instance. So for example, when we have our data set and the order matters in some machine learning algorithm, and they can perform that poorly. So what we need to do is, before we train our machine learning, we need to shuffle the data set. In that way, we do not actually give the algorithm some kind of answer or hints, so the algorithm can just try to learn directly from the data without considering the order of the data set. So this is basically, we want to shuffle the data. So using NumPy, we can create an index here using random permutation of index digits and save them into this variable. And we have the X train and Y train here. This will shuffle the X train and X train. So this is basically shuffling the data. And why we shuffle the data, as I said, is just to remove the order of the training instance, because a machine learning algorithm take into cognizance the order of the training and training set. All right, any question before we move on? Right, so if there isn't any question, as I mentioned previously, if your data set is not divided, as we said, the MNIST data set is already divided into test set and stuff. But if your data set, you have a data set that comes with you, then you can use this function from Scikit-Learn, train test splits, and you provide the data set like in form of an array, and you provide the training side and stuff like that. And when you do that, you can provide the shuffle. So you don't need to do these steps to shuffle the data after dividing the data into train and test set. When you have a single data set, you can create the data set, and at the same time, you can shuffle the data set. When you provide this argument shuffle equals to true. So this is basically when your data set is not dividable. We are like the reason why we do shuffling separately is that our data set is already divided, and we do the shuffling first. Yeah. So, any question? Right. So without further much question, let's move on. So let's look at have now our data set for training set and test set. Then the next set is to do the classification. So let's look at this sample of binary classifier, which is one of the classification we see the binary class, which do classification of true or false. That is based on two binary format. So we're going to look at a toy example that do classify digit into it is 5 or it is not 5. So here, if we look at it, we have Y train. Then here, what we have here, because we only pick or where 5 is and Y test also, therefore Y train 5. And so we subset our Y test and Y train. We subset them here and we have only those with 5. So we want to use this as our sample, our train data to see whether we can train machine learning algorithm whereby if it is true, it would return that yes, it is 5. If it is not 5, it will say it is false. So, but what algorithm are we going to use? There are many algorithms to do for classification, but for purely binary classification, here we're going to use stochastic gradient descent classifier, which basically do kind of classifier classification, but also it does some regression. And they also say that SGD does not fall into merely any kind of machine learning models, like we can say Swabber and Swabber, but it is just an optimization algorithm or techniques that is used to train a model. And it's basically, we can have an instance from Scikit-Learn SDG classifier or SDG regressor. This one can do classification and this one can do regression tags using the Scikit-Learn API. And this one, basically the SDGs classifier is equals to logistic regression, which is fitted via SGG. So basically logistic regression that does classification is this one. And also here, these are just implementation of Scikit-Learn that shows us the equivalence of those. But the SGG is very efficient algorithm techniques and easy to implement, but it does have many hyperparameters and also is sensitive to future scaling. So let me see. Am I showing my browser?
Mm-hmm.
Okay. So I think, yeah. So this is SDG classifier. And as we can see here, linear classifier, SVM logistics with SG. So all this stuff, SVM logistics can be implemented with stochastic gradient descent. So basically, they said it does have a lot of, you can see regularization parameters. And here also, we need to define the iteration, the maximum iteration, and also this stopping criteria when it is doing the iteration. So it does have many parameters to do classification. So that's why here is they said efficient and easy to implement, but SGD require a number of hyperparameters such as regularization and number of iteration. And yeah, so let's look at how we can easily implement that one using Scikit-Learn. So basically, as usual, we import this SG classifier, and we, as you can see here, we want to train. We want to we need to specify the maximum number of iterations. As you can see here, this is the random state, as we always do for reproducibility, and this is the stopping criteria. When will this classifier stop while training? So this is the stopping criteria. So when we define this, then we can fit our classifier. So YX train and Y train 5 that we specify, and we can see that here it takes this time to actually do that. So the SDG classifier relies on randomness during training. That is why it is called stochastic gradient. And that is why we provide the parameter of random steps so that we can have reproducibility. And here, as you can see now, after we feed the classifier, we can now try to do some prediction. So here we say some digit, we specify some digit, which is x naught, and we know that x naught is 5 from the previous section when we saw the data. And now having does that, since we already fit this one, we can call this one SGD predict some digit, which is what we divide here. And here it tells us which is true, because we train based, it is 5. If it is not 5, for example, here we can say it is 1, 11, and when we run, this. Yeah, so here it is not true. I think when we have this one, yeah, it's giving us I don't know, it's not returning whether it is true or false.
Do you need to add a print command or something like that? I'm just wondering because you don't have.
Yeah, but okay, here, you mean here, right?
Something like that. I mean, I might be completely wrong, but I'm just, because I feel like the predict doesn't. Yeah.
Yeah.
Okay. Don't know. Sorry.
Okay. All right. So, yeah. So that is a simple. Oh, gosh. All right. That is a simple binary classifier. Yeah. So the next thing is performance measures. So when we do classification, we try to measure how our classification task performs. Does it perform well or not? So one approach to do that is to divide your data into 3 sets, which is train, validation, and test set, whereby in training set, you train your model and now try to validate on validation set and use the test set for final stuff. Oh, my battery is getting low. Let me pick my charger. Excuse me, please. Okay, so yeah, so to measure the performance, we said one approach is to divide your data into train, validation, and test set. So the training, say you do the training, validation, you do the validation of the data, and finally you hold out this last part, which is test set, to do the final testing of the performance of your machine learning algorithm. But this dividing the 3 into 3 different sets, what it does, it actually reduces the number of your samples you have. So it may not actually, and we know sometimes the more data you have, the more accuracy you have. So when you divide your data into train, validation, and test, you reduce the sample size. So one solution for you is for us to do cross validation, which is basically used to estimate the skill of machine learning model. So cross validation allow us to divide our data set. Okay, I have example here. So this is cross validation. So if we have a data set, we can divide it into 5 sets, 1, 2, 3, 4, 5. And what we do is like the first fold, that is called fold. We train on this set and we validate and we test on the last one. We take the next iteration, we train on the fourth and test on another one. We train And finally, we take the average of error of all the 5-fold, and thus give us the what we call cross-validation. And one of the main, or it is called CB, and we call K-fold CB. One of the K widely used is 10. That is why mostly you will hear 10-fold cross-validation. So 10-fold cross-validation is one of the widely used validation techniques. Yeah, I don't know the theoretical background behind that, but it's one of the most widely used. So how can we do that with Scikit-Learn? Since we said this approach, dividing the trained, validated, and tested is less optimal, this is the way to do that using cross. So we import using from model selection, we import cross-validation score, and using cross-validation score, we feed in our classifier, and this is the X10 and Y10 5, and you provide the CV, the how many fold you want. So we want 3-fold. If we want to 10, we can give 10-fold, and this accuracy here is scoring is accuracy. So if you look at it here, what is this? The CLF is our classifier here that we train. Can you see it? That we train, and here is the X10. Is basically your training sample, and here is your target, and here is your validation. So here we can see that what it will return is the error or the accuracy on all the validation set. So you can see we have 3, then this the accuracy 1, 2, 3. So we have 3. So as you can see that this accuracy is somehow encouraging. I mean, the classifier is somehow a high percentage, 96%, which or 97, I can say. So there is some talk in the book which he said accuracy is generally not the preferred performance measure for classifiers, especially when you are dealing with skewed data set. So here, as you can see, the accuracy we are using is not preferred performance, even though we are using cross-validation. So when you are using cross-validation, sometimes is when you have not skewed data set, you have balanced data set. But what if you have skewed data set that you don't have equal representation? In that case, using accuracy is not a good idea. So there is what it suggests. Okay, here is, yeah. So what we're gonna see here is another performance measure that can deal with issue even if you have skewed data set. And here is actually cross-validation implementation from Scratch, which we may not necessarily need. I may not go through this one because of time. Yeah, so the next one, which is confusion matrix, basically is a much better way to evaluate the performance of classifier. And what it does, this confusion matrix is just try to count the number of times instance of class A classified as class B. In another way, it's trying to find how many mistakes a classifier does. Instead for it to say this is A, it says this is B. Or instead of it to say this is B, it says this is A. So it tries to count those numbers, and from those numbers, it can say that this is actually the performance. So the implementation of confusion matrix, just like we see cross-validation score from Scikit-Learn, we also use cross-validation predict matrix to perform K-fold cross-validation, but instead of returning evaluation score, it returns prediction made on each text fold. So here, what we mean by that is instead of returning the evaluation score here, as we can see the evaluation score on each fold, here we have the evaluation score on each fold. Using cross-validate predict returns prediction made on each score. So in each fold, so let's look at it. So here we can import our cross-predict, And here we can have cross-val predict, the same thing as previously we provide the CV, but remember here in the first one, we provide the scoring, which is accuracy. That is where we have here the accuracy on each fold. But here we are not providing accuracy, but it just gonna provide the prediction on each fold. So here we provide the prediction. This is Y-trend predict. As you can see, this is a prediction that it provides for each CV. So thereafter, we use the function confusion matrix to actually calculate the confusion matrix. So here we can import the confusion matrix from the Scikit-Learn matrix, import confusion matrix, and this is a function called confusion matrix where we have Y-trend 5 and Y-trend predict. You can see that Y-trend 5 is what we have been using first, and this is Y-trend predict, and this gives us the this is basically the confusion matrix. So let me have maybe, yeah. So I think we may have also already have the idea what confusion matrix is. So this is an example of confusion matrix whereby we have true class, we have the predicted class here, and the true class here we have true positive. So where the our classifier actually classify something which is correct, and we have true negative, which our classifier classifies something which is true, but it says it's not correct. This is false negative, and this is false positive. Right. So,
sorry, can I just ask a question quickly?
Yes.
Do we know with Scikit-Learn, like whether the rows are, the predicted labels or the actual labels, or whether it's vice versa? Because I just see, that example you showed.
You say what?
So I think could you go back to the example of the confusion matrix you showed?
Mm-hmm.
I mean the like on in your browser. Sorry. Yeah. Thank you. Yeah, because I was gonna say, so here like the the rows are like, or the along the Y, I guess, it's predicted on the left, and then the true class along the top. But I mean, I was just checking in the book. It's the other way around. I don't know. Does anyone know off the top of their heads for Scikit-Learn which way around it is? Or
yeah. So if you look at it, this is also another example which is predicted. This is so. If you look at it here, this one.
Yeah.
So if we look at that here, this is the first row and this is the second. Mm-hmm. So here it explains each row in a confusion matrix represent an actual class. So each row, while each column represent predicted class. So this is how it is. So in the book, this is how it is, not this case. So this is the one actually we should have shown. So this is the this is the predicted, this is the actual. So each row in confusion might represent an actual class, while each column represents a predicted class. So if we look at this one here, the first row of this consider non-5 images, that is negative class. These of them were correctly classified. If you look at this one here, which is true positive, right? Correctly classified as where the others are classified, this one as non-5s. The second row consider the image of 5 as positive class. So here we have the different classes, and we are correctly classified. So basically, this is shows how each confusion matrix is. So I don't know why the confusion matrix is sometimes represented in this format. Does anyone knows why? But the book actually showed this structure. So I don't know why. Sometimes does anybody knows, because in some instance you can see that it is represented at this, but I think the Scikit-Learn actually what it is actually using this format. Can anybody shed more light on this?
No, I guess it just, I mean, it represents the same thing. It's just you're just swapping it around. So I think I was just curious which way around it was for sure with Scikit-Learn, but yeah, I realized I should have read your bullet points before asking the question. But yeah, no, that's really helpful.
Okay.
Yeah, thank you.
Yeah. Mm-hmm. So When we have a perfect classifier, it will have these diagonals to be 0, 0. It means everything is predicted correctly. So that's why here a perfect classifier will have only true positive and true negative. That is, anything that is not 5 will be classified. Anything that is 5 will be classified as 5. That is only true positive and true negative. So its confusion matrix will have non-zero values along its main diagonal. So if you look at this one here, what we do here, Y-trend perfect prediction, we just simply use this variable and assign it to the same, to a new variable here. And we just call this confusion matrix in the same Y-trend file. So we can see that this is perfect. It just predicts everything is correct here. So this is basically about the confusion matrix. Yeah, right. All right. Okay. So any question about confusion matrix? Okay. So let's move on. The next one is precision and recall. So sometimes, as you can see here, is sometimes we may need to combine be more precise or concise metric rather than just confusion metrics, because the confusion metric is not somehow concise in the sense that you need to look at what it gives you and stuff like that. But we may need to have a single number which is so precise in nature. That brings us to precision and recall. So an interesting one is one accuracy of the positive prediction is called precision of the classifier. That is how the classifier is identifies positive predictions. So precision is given by this, which is TP, number of true positive, FP is the number of false positive. And also the recall is sometimes called sensitivity or true positive rate. Is the ratio of positive instances that are correctly detected by the classifier. So these two are also used to measure the performance of our classifier. So the first one we have seen is to use confusion matrix. Now here, this one. And this one, it is somehow concise. It brings how our classifier how our classifier give precise prediction or true prediction. And to do that, basically the SEMs you import from matrix, and we have this precision score, we have this called recall score, and when we call this precision score, we can have precision of our classifier here. Where we have the Y-trend 5 and Y-trend pred we have. So this is a prediction we did. And also you can do that manually, because we said, looking at this one here, where is our confusion matrix? Okay, so when we look at the confusion matrix here, we can see that we have this, the first row, the second row. So what we can do is we can calculate this manually. You can see here confusion matrix is this. We can use this one to actually fit whatever inside the confusion matrix and calculate. But this is actually not what we're interested. This is the one that we may be interested that we can just calculate from the Scikit-Learn. This is manually. Also, we can calculate the recall from recall score, where we have this, and this one we calculate this one manually. The next one is F1 score, which actually is the combination of precision and recall. Do we have? Let me see. Time. Oh, we have. Okay. The next one is F1 score, which is basically the combination of both precision and recall into a single metric. And here we're gonna see what F1 score is. Basically the harmonic mean of precision and recall. When we say harmonic mean, is basically the weight value of both the two. and F1 will only be high if both the recall and precision are high. So let's look at because we see that before we have accuracy, which is a single number, and also F1 score here is a single number. But why do we prefer accuracy, F1 rather than accuracy? Because previously we said accuracy is not somehow good. So F1 score takes into account how data is distributed, and it is usable when you have imbalanced classes. If you remember previously, we said the accuracy is not good when you have imbalanced classes. So if you want to have a single accuracy, then F1 score is better when you have classes that are imbalanced. But the disadvantage of F1 score is that it is less interpretability. What about accuracy? Accuracy is easy to understand. It does not take advantage into if data is distributed unevenly. So that is basically the comparison between accuracy and F1 score. So as usual, how can we compute F1 score? So this is how we can compute F1 score. Y-trend, this as always, Y-trend predict, and this is the F1 score. This is calculation manually, and we can see, but we always integrate with this one. All right, so let's quickly, we don't need this. Let's quickly go to, yeah, so another one is called precision and recall trade-off. There is some kind of trade-off between precision and recall. So sometimes people may need to have precision, and in some instance you may need to have to recall, but the two cannot be achieved at the same time. So we need to have a trade-off. So this is an example, and I pick it from the book, which I think is good to look at it. They said, for example, if you train a classifier to detect video that are safe for kids, you will probably prepare a classifier that rejects many good videos. That is, you have low recall, but keeps only safe ones. So high precision, that is safe one. The classifier should always have high precision, rather than classifier that has much higher recall but lower precision. So you can see in this case, you may need high precision but low recall. On another hand, suppose you train a classifier to detect shoplifters on surveillance images. It is probably fine if your classifier has only 30% precision, as long as it has 90% recall, so that it can actually detect recall. Even if it is not, then okay, that's fine. If it is not precise, it's not a shoplifter, then yeah, okay, you can go ahead. But you want the classifier to detect any sense of shoplifting. So you can see we have many kind of trade-off between the precision and recall. So, but you cannot have both the two. So that's why we have what is called precision and recall trade-off. The next one is measure of classification, rock curves. It's another tool for measuring classification performance, and it's called receiver operating characteristic. So how can we calculate the rock curve? So it does have also some kind of theoretical underpinning it, but here is how we can calculate the rock curve. So it is very similar also to precision and recall, but instead of plotting precision versus recall, the rock curve plot the true positive rate against the false positive rate. So this is how rock curves is. What is true positive rate, which is recall, and positive rate, which is actually what it calculates. So I'm not quite sure. I've not checked much about the rock curves, but this is basically I'm not sure when can we use rock curve. As we have seen previously, we can use F1 measures when our data, we have imbalanced data set, and we can use accuracy when we have balanced data set and it's more interpretable, and we can use confusion metrics as well. But I'm not sure when we're gonna use rock curves, but does anyone has a sense of when do we use rock curves?
I definitely don't have a good answer for it, but it seems to be quite commonly used.
Alright.
I feel like when I've gone to kind of data science talks and stuff before, that seems to be the standard thing that people use. I don't really know. I don't have a good explanation for why that is, but
Rock cabs.
yeah,
Hello?
I guess they give more information than the F1,
Okay.
for example.
Yeah.
Oh, seems like I've got a bit of a lag on my side.
Yeah, but yeah, so I'm familiar or see mostly confusion method to calculate the F1 score and precision I recall. That is what have been seen. But F1 rock caps, I'm not sure when it is quite useful. So maybe skip it. Yeah, so this is just explanation about rock cap and also area under the cap, which more or less the same thing. Let's keep that for timing. Okay, so that is about the performance measures we have seen. We can actually have accuracy, we can have confusion matrix, we can have precision article, we can have F1, and we can have rock cap. These are all performance measure of classification, and each one has its when to use, and maybe we can read further. So we have seen now the basic binary classification. The next one is multi-class classification. As I've already said, multi-class allow us to do classification for more than 2 classes. And some algorithm basically allows you to do multi-class, like a random forest ONA-based classifier. They do multi-class classification automatically. But support vector classifier or linear classifier are strictly binary classifiers. So we can see that even machine learning algorithm, some algorithms are inherently multi-class. They can do both multi-class and binary, while some are only binary class. But there are many ways to implement the multi-class classification. Two of the prominent way to implement multi-class classification is 1 versus all and 1 versus 1. So what does that mean? So 1 versus all, train binary class for each digit. So what it does is, like, assume we want to train, we have 10 digits, 1 to 10, and we want to build a classifier. So what we will do is, like, we'll train a binary classifier for zero detector. It means it will detect if it is 0, it says 0, yes, true. If it is not 0, it says false. We implement a 1 classifier for 1 detector. If it is 1, true. If it is not, so we implement that is what is called 1 versus all. So what we mean by 1 versus all is that 1 versus all. So if it is 0, it is yes. Else all, everything, then false. That is 1 versus all. Then we have 1 versus 1 over, train a binary classifier for every field of digit. So what this does is 1 versus 1. So it will train a classifier between 2 digits. For instance, 1 and 0 and 1. So if it is 0, it says 0. If it is 1, it says, so it trained between 2 digits. That is 1 versus 1. So this is multi-class classification. So this multi-class classification is an example of how we can classify digit from 0 to 10. So from 0 to 9, I mean. So we can use this 1 versus all, to classify digit from 0 to 9 using 0 detector. We can use 1 versus all to classify digit from 0 to 9, but using this approach. So let's look at an example on 1 versus 1 classifier, which is basically from Scikit-Learn. So thank God Scikit-Learn has a consistent API that almost everything is the same. What I mean by that is just what you need to do is just to import the models you need. The API has some kind of consistency. So as previously, we can import the 1 versus 1 classifier, and we can train it here, and we can fit it. So the first thing we can train, fit it, and predict. So we can see here some digit where we have, if you remember, some digit is 5, the first digit, which is not, which is this. So you can see our classifier actually predict that it's 5. But also, what this does is this. So 1 versus 1 classifier. All right. So let me see how it. Let's see. So 1 versus 1. All right. So what it does is this: 1 versus 1 classifier is that when it does the classification, it calls what is called decision function to make decision what kind of digit is that. So if you look at this one here, when we call the classifier here over our classifier here, we call a decision function and we put some digit here. So here decision function, you can see it will turn, we have the decision score. The first one here, we have this one, because we have 10 digit, but this is only 1 digit. So these are the decisions that shows which digit that based on the probability. This decision is somehow kind of showing how it is. So here, this is it, this is this one, but the highest decision is the one that says which classifier is that. So we can see that this one, we have 0, 1, 2, 3, 4, 5. So this is actually 5. That is why here we can see that, all right. So the highest decision determine which, what our prediction will be. So here, as you can see here, is 5. So if we look at this one here over classes, when we look at this classes 5, then it shows that yes, of course, it is 5 that we predict here. Right. So this is basically what this 1 versus 1 classifier does. This is basically what is behind the scene, showing automatically here when we do this, it predicts it is 5. But here we are showing how the classifier make decision to say that the result is 5. This some digit is 5. So this is how it makes decision. So the way it makes decision is we can call this function decision function, and what it will return an array with the I don't know, this is not probability, right? I don't know what this is, the number, but the higher the number, it tells at what digit it does. So we can see that this is 9.333. So it's, the accuracy here is large enough. It's saying that this is 5 because the classes, we have 10 classes if you look at it, because 1, 2 up to 10, and therefore this is 5. So this is how an example. But also we can, as we said here, random forest classifier can do multi-class classification. So in this case, we can actually use random forest to do multi-classification. So here you can see here, forest, we can actually call use random forest to do classification, which basically does the same thing as previous one. You can see here we fit, and forest class we fit, we predict, and we have this. And the same thing here where we have decisions, it shows one here, but here use a random forest, we can see the probabilities here. Forest classifier produces the digit, and we can see that the probabilities here is there is one here from the book. If you look at it in the book, there is 0.9 here, which has the highest probability, which is the 5th one. That is where it shows, of course, it is 5. So that is an example of let's quickly move on to this time. Okay, we have, all right. We have the next one, multi-level classification. So having looked at multi-class, what multi-level is. So an example of multi-level classifier is this from the book. They said when we train an algorithm to recognize, for example, 3 faces, Alice, Bob, and Charles. And when we actually train the model and we have this kind of output, then we can see we have multi-level. For instance, here we have, when we show the algorithm, maybe Alice and Charles, we have multi-level here. So this multiple binary multi-level classification system. And one of the algorithms that support multi-level classification is Keras neighbor classifier. But not all straits for classifier support multi-level. So this is an example of multi-level classification. I don't really, on top of my head, think of the real life example of multi-level classifier, but this is just an example of the book. But multi-class is something that we see every day. So this is an example. We import the Keras neighbor, and we have Y-train large. So Y-train large here, as you can see, is this is just something, anything greater than 7. So this shows us 7, 8, or 9. And we create another one, Y-train odd, which is odd number, indicate odd number. Now we have Y multi-level. So here we have multi-level in the sense that we use NumPy to concatenate this and this. Then we have Y-train large and Y-train odd. So this means that we're gonna have an algorithm that can predict whether this is large, is something that is greater than or equal to 7, or something that is odd. So you can see this is not multi-class but multi-level. So there's something using consistent API for Scikit-Learn, we can do the training and we can fit. You can see this is the train and this is the multi-level we fit. So after we fit, then we can do prediction with some digit. So some digit is 5. So we can see that here, this is false because this is 5 is not greater than or equal to 7, but this is true because 5 is odd number. So this is multi-level. We have many levels of our classification, not multi-class. Yeah. So any question before we proceed? Do we have more time? Oh, we are running out of time. But there's something we evaluate classifier. We can also use F1 score to evaluate multi-level classifier. As you can see here, in F1 score, we make prediction using CV3, and now we call the F1 score, as you can see, and use the average micro average, which basically take the average of the prediction. So this is basically how to, it's the same as how we evaluate the other classifiers. The last one, which is multi-out classification, which is really, I haven't even know about this one also until this chapter, is somehow generalization of multi-level classification, where each level can have more than two possible values. So in the previous one, we see multi-level. We have level whether this one, this level is either greater than or equal to 7, or this level is odd. But what they mean here, these levels, is that each level here can have more than 1 or 2. Each level can have more than 1 or 2. That is multi-output. So here they said, so this they give an example. An example is a system that removes noise from image. It will take as input a noisy digit image, and it will output clean image. So if you look at it here, let's go there. An example is a system that removes noise from image. So we are given an image and we added noise, and we want to remove the noise, and we want to actually have the image from it. In this case, this class output is multi-level. Why it is multi-level? And each level can have multiple values. So in this case, because this is image, each level, 1 level per pixel, and each pixel has this intensity from 0 to 255. So this is what they mean by that instance. So let's look at an example of multi-output classification. So this is an example. We just use NumPy to create a noise based on the length of the trained data. And we add noise to our trained data. So we add the noise here. We have where we have mode. And now we use the random noise to add to create a noise in the text, and we add noise to text where we have text mode. So here we have white mode and we have white text mode. So let's look at an example how this is done. But before that, let's look at how the noise, what we mean by the noise. So if you look at this one here, we want to just look at the test data. So if you look at this one here, we have X text mode. If you look at it, the one with noise. So now here we want to plot it, X text mode, and this is some index here. And here is Y text mode. If you look at the Y text mode, it's just X text, which is the original, which is something that is not. So we just plug them. So you can see here the something with noise. This one is something without noise because it's just the test set. So we want to train a classifier to predict, given the noise, to predict this one, to the true value. So that is what we want to do here. So this is the classifier, which is KNN classifier to fit, which we have already trained. We're going to fit it one here, which is white train, X train mode and white train mode. And this one is the one with the noise, and white train mode without the noise. And here we make the prediction on the text, which is the X mode. And we can see here, it actually we have the prediction on the text data, which give us 7. So, it's exactly 7. We have exactly spent 1 hour. So this is basically an example on how to make the prediction on the multi-out classification. So I'm not quite sure also on top of my head when this will be useful in real world and real life classification, the multi-out classification. I don't know if someone has more information about that that can talk about it. Does anybody has an experience with this multi-out classification? So yeah, yeah.
Yeah, I mean, I was going to say, maybe because I haven't fully got my head around the concept yet, but it does feel like this would be used mostly with images than any other type of data, really.
Yes.
But yeah, it was interesting to see it work though. That was pretty cool. The visualization they gave us. So
yeah. All right. So this is the end of my presentation. Thank you all for listening. Any question? Yeah.
Thank you. That was really concise.
Yeah.
Yeah. I think I find this.
What are you using for? I was just going to ask what are you using for your Jupyter notebook?
Me. Okay. It's
it looks really cool.
Okay. This one. What do you call it? VS Code.
Oh.
Yeah, it's VS Code. So now VS Code has this extension that allows you to use Jupyter Notebook in VS Code, because like I don't like using the Jupyter Notebook from my browser because it's somehow distracting for me. I just always Google when I was working. I would just be Googling. So inside the VS Code, let me show. So, all right. So let me see something. Let me share my screen. All right, okay. So let me share my screen again. Am I sharing my screen?
Mm-hmm.
All right, so you can see this is VS Code. These are the stuff like that. So VS Code actually allows you to, now, not previously, now it does have this extension that you can use Jupyter notebooks on the VS Code and stuff like that. It's nice. It's quite good. One cool thing with that is also you can have remote session if you have remote server. For instance, now in using Google, what do you call this? Google that gives you the Colab, Google Colab. So if you have remote server, you can have remote session. For me, like I usually have remote session. I connect my remote server. I run my code. So I don't need to use Google Colab if you have, so you can do that. So this is really cool. Yeah, you can try it.
Yeah, I'll definitely check it out. Thanks.
Right.
You were going to ask something, Sam?
Oh yeah, to be honest, that actually came to my head at the start. I wasn't going to ask you that as well. No, I think I was mainly just going to say, I mean, there's a lot of material in these early chapters, so I think it was nice to be able to give like a good overview of all of the different types. So yeah, that was it for me really, I guess. Yeah, it was just to say it was a nice presentation and thank you.
Oh, yeah, thank you very much for listening. It's not quite good for the, but yeah, I try.
It's good. I mean, I enjoyed it. So
yeah, me too.
Yeah,
that was really well presented.
Yeah.
All right, thank you very much. So the next one is Arturo, right? Your presentation on the next one. Okay,
yeah,
cool.
Next time.
Yeah. All right.
Get a bit started.
Yeah, I haven't checked the sign up for a while. I think we're still empty for the week after, for the session afterwards. But I think we should. I'll follow up in the chat because I think
Okay.
I was looking a few chapters ahead. I think it's might be chapter like 6 or 7 is really short, and maybe we could think about combining some of them. But I think we can decide that later.
All right.
I'm just super busy at the moment, so I have to hopefully once we get past mid-June, I'll be able to start presenting again. But yeah, cool.
All right.
Yeah. Thanks again.
All right. Thank you.
Good to see everyone as well.
See you next. All right. Bye bye.